Hello, everyone. Welcome back after the last networking break. So we've now got Anthony Lorella from Maya HTT, and he's going to be talking about system simulation for the development of offshore assets. Over to you, Anthony.
Thank you very much. And thank you everyone for joining us today. As we said, the topic of discussion is going to be around system simulation, specifically for the development. So that would be the design and analysis of offshore assets. Um, in the context today of what we'll be discussing, you'll see it's going to be also, I think, based on you might have read it in the description for this session, but it's going to be in the context of green hydrogen production. So we'll get more into what that means in just a second. But for the most part, that's the overarching theme for today's presentation. So before we get started, maybe a little bit about Maya HTT. At Maya, we help organizations generally with their digital transformation journey. So for that purpose, we are not just a consulting business or a systems integrator, but we are also a software developer. So we work with or model, excuse me, we develop 30 modules, over 30 modules for Siemens, which is used by millions of engineers and as many companies worldwide. Siemens themselves has recognized us as a top global partner in multiple years, but most recently 2023. So we're partnered with Siemens on a lot of that. And in terms of Maya itself, over 75% of our team are actually scientists and engineers with a lot of hands-on experience from the team that would span nearly every industry. Um, so outside of that, if you're an organization that's looking to better design, better simulate, improve your manufacturing processes, or just optimize your overall operations, our combined expertise and the engineering software we provide, the software development side, and also our unique AI expertise positions us really well to help you move from things like concept to a completed project and even beyond that. So, a little bit about myself. You already heard my name is Anthony Lorella. I have been a simulation specialist at MyHTT since 2015. My background is in mechatronics and system simulation, and that's across multiple industries. And I've received my Bachelor's of Engineering from McGill University, which is in Montreal, Quebec, where I live now and where our Canadian headquarters is at Maya. So, on to the kind of topic of today's discussion. Generally, like I said, we're looking at the development of offshore assets specifically for the production of green hydrogen. Um, as a lead into that topic, there's a lot of different motivations that would bring us to explore the different energy sources that we are, from obviously reducing emissions to de-risking operations and saving on operating costs. For all of those different things, simulation has a part to play and can allow us to innovate. One of the main goals generally for simulation is to increase the efficiency of the design process and allow engineers and analysts to understand the behavior of their system early in the cycle and make informed decisions. Ultimately, the end effect of that process would be reducing things like capital expenditure in the process of building and commissioning equipment, but also reducing overall operating expenditure, which comes from running it. And we'll have a look at how that comes into play in just a second. Um, so in order to generate this kind of green energy, the green hydrogen we're talking about, specifically green hydrogen being the one that's coming from renewable sources, several sources can be considered. So in this case, we have things like wind turbines, solar panels, maybe some that are less common, like wave converters, for example. And to improve the efficiency, these different energy sources can be mixed together to improve, like I said, both performance but also reliability. Um, and this energy can be used directly, but the power demand of production doesn't necessarily always correspond to the fluctuating power coming in from those sources. Obviously, all of those are dependent on weather patterns, um, and so they are not going to be consistent. But energy storage is also possible. So for this purpose, we're going to be using an electrolyzer to be able to produce hydrogen and then also system to pressurize and store it for later usage. So from end to end, those are the systems that we'll be looking at today. We can, in terms of what we describe as a digital twin, we could pretty much extend the capabilities of simulation to all parts of the hydrogen production and distribution process. But from what I described just a second ago, really our main focus is going to be everything in the orange box that you see here, up to and not necessarily including the micro scale power generation that would be like fuel cells or things like that, whether those are transportation based or stationary. So more like the boxes you see here, up to and including storage and distribution. So, like I said, we're using multiple energy sources. We're combining with electrolysis and hydrogen compression. This makes the system, or the part of the system that we've framed in our question here, quite complex, and it involves a lot of different physics. So that's typically an application where simulation can become very useful. We can capture the behavior of each subsystem in order to better integrate and control them. The idea would be to predict interactions and improve the global performance. All the questions you see here are examples of questions that can be answered with simulation. So how can I predict the quantity of electric power that I generate with solar panels? Same goes for wind turbines or wave converters. How do I size the system right now to adapt to my production needs? How do I modify that if my production needs change? How do I, size the hydrogen storage? And so on and so forth. There's a lot more that we can consider, but you get the idea from some of these questions, and these are all questions that ultimately can lead to being answered by a simulation model. So the models themselves are dynamic and complex. That's kind of what it boils down to. When we look at systems simulation, they're very well suited to dynamic and complex systems. And when I say complex, what I mean is multi-physics. So when we talk about system simulation, or sometimes referred to as 1D simulation, we are talking about usually the intersection of a lot of different physics. In this case, for example, we're looking at fluids, thermal electrics, um, mechanical systems as well, and also the controls that will go in and form all of those. So um, there's a lot of challenges with that, but system simulation is positioned very well to answer all of those challenges. Uh, Obviously, we have the ability, like I said, to combine all of these physics in one model. The way we do this specifically with our system simulation tools is using uh, ready to use off the shelf components that are validated by the developers and engineers. And those span various libraries, which we'll see in just a second. Um, the models themselves are, like I said, dynamic in nature. So those are off the shelf components which have the equations of physics behind them, and those are the transient behavior equations of physics for all of the different components that you would need across those different physics domains. There's also handy post-processing tools that allow you to go and, after an analysis, make a good informed decision on the overall behavior of the system. So in a bit more detail for system simulation, these tools can be used for many different applications and industries, which you see here. Those multi-physics libraries that I was talking about are you kind of listed. Some of the major ones are listed here, but they cover a lot of the different basic physics that you would need for any type of system. And within them, we have over 6,000 validated multi-physics models that you can use and put together to build pretty much anything. There are different levels of complexity, so this can be used at multiple points in a project at different levels of maturity for either pre-design all the way down to performance optimization and controls validation. And then there are a few extended uses, things like interfacing with other code like CFD. The PLC interface capability makes it possible to couple these system simulation models with PLC or automation code, either in a software in the loop or hardware in the loop environment, depending if you have a real or emulated PLC that you need to virtually validate. There's a lot of other interfaces and capabilities, but those are some of the bigger ones that we can cover in a bit more detail in just a second. So onto the model that we're talking about, for the purposes of the green hydrogen production. In this case, this is a large-scale overview of all the different subcomponents that are in our offshore hydrogen production um, asset. So this one includes, like I said, 3 different green energy sources: wind turbines, solar panels, and the wave converter. These are feeding power to an electrolyzer, and then that will produce hydrogen, which will go to our pressurization and storage subsystem. Our focus will be on the 3 energy sources and how they behave, and how, in the end, those can influence the production of hydrogen overall. So the first on the list is the wind turbine, and this is a view inside of that subcomponent, what those libraries allow you to build. And that's what we see over here on the right, is what's actually being produced with those library components. This subcomponent obviously allows you to predict the energy or power that's generated by capturing the energy of the wind. In terms of what we can model and use, this allows us to define the number of wind turbines we want to use, um, the definition of the overall geometry, things like fan diameter, pitch, angle, gear ratio if we need it, and then also the generator performance, because the generator itself as an electric machine is being modeled here as well. And then we can also bake in a lot of more intelligence. Like you see here, we actually have some feedback loop that has active pitch control on the fan blades. So that's an overall example of what we have. You can see a number of other things that I could highlight, like the color coding of the different physics in the models and things like that. And that carries over to the other subsystems as well. But these are all built from off-the-shelf components that we have across the different physics libraries in our system simulation tool. Returning now to the overall system, we'll turn our focus to the solar panels. The solar panels built in much the same way with different physics that you can see here based on the different color coding. It's also a subcomponent that allows you to predict the power generated, but in this case, based on the obviously position and intensity of the sun. The models, like I said, are transient in nature. So what we can do here is not only worry about the composition of the solar panel, so in terms of how many cells and how many panels in an array actually are existing, but also the emissivity of the surface, and most importantly, the changing position of the sun over time, which is something that we can simulate based on the data that's within this tool. So we have the ability to predict, based on time and position, the overall incidence angle of the sun with the panel. Uh, Lastly, we can look at the wave converter. And the wave converter is a bit more of a complex system, but it mostly contains hydraulic equipment, in the fluid domain, and that's a library that we also master quite well. So things like pistons, valves, the hydraulic motor, ultimately that everything's feeding, connecting to the generator, and all the different hydraulic equipment is also modeled using our off-the-shelf components. But this is a much more detailed architecture, but something that we still master quite well in system simulation, allowing us to basically capture the transient operating conditions from the wave patterns, that being wave frequency and the wave geometry. So if we put all of these together and connect them to the electrolyzer and the storage, as well as give it some weather patterns that we can grab pretty much from anywhere and import into the model, we can make some predictions in terms of the annual performance of the overall system, both in energy storage, but also energy consumption of the electrolyzer and overall hydrogen production. And like I said, these are system models or 1D models, so they're quite lightweight and the simulation is very efficient. So that means that these simulations themselves actually only take on the order of seconds to minutes to simulate what is effectively an entire year's worth of operation. And then we can use that post-processing I was talking about to make informed decisions on things like what is the overall kind of contributor to the green energy production. In this case, we could see here wind energy is the winner overall, but we also have more detailed reporting that allows us to see that although wind energy overall is the winner, um, different months of the year, we actually have different energy sources, which are the overall larger contributor. So that's important for our understanding of how the system operates and what the critical parts are. Likewise, because these models are quick to run, we have the ability to simulate multiple different changes or multiple architectures. So in this case, we could see here overlapping performance spider charts of different system architectures based on criteria like energy import, hydrogen storage, and the CO2 rating, and even cost if we were interested in modeling the cost of the system. Extending the uses a little bit, I talked about the ability to connect with PLC, and that's certainly a capability of these models. They allow us to do what we call virtual commissioning, where we connect either emulated or real controls code on hardware or on a computer against a virtual version of the plant, where we can do some commissioning before we even bring things up and running on the field, which can save us, costly downtime and save us on the actual physical commissioning time. Likewise, another extended feature of models like these is the ability to act as virtual sensors for remote monitoring of equipment. So for example, the simulation models can be configured to take in real-time data from the field, be fed into the model, and make predictions as far as performance of components that do not otherwise have sensors outfitted to them. So that could be for reasons like it's too intrusive or just plain costly that we don't want to put sensors in. These models will be able to give us predictions of the state of various equipment. Not only that, but if we want to use kind of web-based monitoring tools, these can act as what we call an executable digital twin, allowing us to make predictions based on the simulated future state of the equipment. Finally, there's a lot of different other applications that we can get into for system simulation, things like modeling compressed and cryogenic storage tanks, uh, aero gas turbine performance for hydrogen-based gas turbines. Likewise for combustion engines, the actual combustion process, the after treatment, the injection of the hydrogen, and also very importantly, the design and analysis of the fuel cells, which are actually going to consume this hydrogen and generate the power later on. So just to conclude here, we looked at system simulation specifically to help address challenges of green hydrogen production. Those multi-physics libraries make it possible to model the whole system, allowing us to size the subsystems and understand the operation of them. We can better integrate them together because all of those physics can be modeled in one system, allowing us to get a better understanding in terms of overall behavior, but also the post-processing can let us make very good use of the data to understand more minute operating details. And then also we can evaluate virtually control strategies via the PLC connection that I was talking about. Finally, all of this obviously allows us to do things like reducing the amount of iteration, right? Selecting the best design on the first try, reducing risks, and accelerating a project overall. So that's everything that I had to share with you today. My information is here, and alongside that are QR codes that you could scan if you're interested for things like free trials of the software we provide to do this. Or over there is the one that you can scan if you want to book a meeting to discuss this or anything related any further as well. So I'll leave those up right now, and I think we can also move on to questions.
Yeah, thank you, Anthony. Yeah, we've got a couple of questions. The first one, can these system models be used in real-time monitoring of assets in the field?
Yeah. So that executable digital twin I was talking about gives us the ability to do that real-time monitoring. We can also have kind of export these to a more lightweight format so that they can actually live on top of hardware that can be used pretty much anywhere.
Cool, thank you. Next question, can other energy sources be considered? What other subsystems can be modeled?
Yeah, so if I go back to those libraries I was talking about, they're quite extensive and they really cover fundamental physics. So pretty much anything you wanted could be modeled with those libraries, especially because they give us the ability to go in and modify anything from the ground up. So if you wanted to develop anything even more novel than what we have already, you would be free to do so. So there's quite an open tool for that.
Cool, thank you. And then the final one is, what other parts of the hydrogen ecosystem can be modeled with the system simulation?
So I briefly touched on a couple of things. We looked at production to storage, but if I go back to that schematic that I showed earlier, or if I recall, there is also the distribution at a large scale. So if we talk about kind of like large pipelines, transportation of the hydrogen over long distances, the different considerations that go along with that. Um, and obviously the consumption of the hydrogen with those fuel cells, like I said, are all possibilities with a tool like this.
Cool. Yeah, that's it for the questions. So thank you very much, Anthony. A great presentation.
Right.
Thank
Well,
you.
thank you very much, and have a good day.
Cheers.